Okay.
David.
I'm having some.
Oh, okay.
Not possible, don't worry. No, there's not a test at the end.
All right, so shall we get started? Okay, so welcome everyone. It is my pleasure to introduce Dr. Nigam Shah, who is an associate professor of medicine, Stanford University, and a core member of the biomedical informatics graduate. So today he will tell us about AI and machine learning shaping the future of healthcare. Thank you, Nigam.
Thank you. All right, so this is my third visit to ISI, and every time I come, I keep finding new people who I didn't know existed and work here. Previously, I always thought ISI to be a place that did ontologies because that's what I came here for, and I only met people who did ontology. And now I'm meeting people who are doing machine learning and so on. So it's always a fun to be here. And the way I'm going to structure today's talk is I have about 8 or 9 slides of how I think machine learning can help healthcare. That is sort of the main content of the talk. That gives a frame of reference about how I believe AI can help. And then I have a few examples of my own research traversing that space that I'll lay out. And in terms of timing and everything, the first part is the most important. The examples in my group are kind of point solutions that individual faculty member does, so you can check out the email, whatever. All right, so let's get started. I'll give you a one-slide overview of what motivates what we're going to talk about in the lab. If you search around on the web, most likely you will arrive at the conclusion that my group analyzes electronic health records, which is by and large true. We work with data of about 8 million lives of EHR, about 200 million lives worth of claims, and then a few funky data sets such as search logs of what doctors search for on uptodate.com for the whole of the United States. It's kind of amazing what doctors search for in July and August. That's when the new residents come. And so you do not want to be in a hospital in July and August. We've dealt with some other odd data sets, such as the search behavior of individuals on their phones and their subsequent health service utilization, trying to predict 60-day utilization based on what they're searching for, where, what apps they have and time of day, and 500 other such variables. And the bulk of the work sort of falls into 3 buckets. The first is to answer clinical questions, a specific question about a patient in front of you, and how should you manage that patient. At any given point, we'll be running 10, 15 of these, and the natural culmination of that today is that we run the country's only bedside service. But if a treating physician at Stanford has a question about what to do for a given case, we can produce a 3-page summary of what happened to similar patients in our data as well as in the Truven market standpoint. I don't think there's any other hospital, academic medical center that has such a service. And the idea being that if you're unsure of what to do, why not hold the collective practice of your fellow clinicians as opposed to the 4 or 5 that you can actually physically speak with. The second bucket is about asking questions that doctors don't ask. How many of you have heard about polypharmacy? Okay. How many of you heard about Medicare? Okay, a couple. So Medicare is, for mostly people above 65. There's a conversation typically in the Medicare space about seniors taking too many drugs, 5, 6, 7 drugs. Next time you go to a doctor, ask them what is the most common 6-drug combination in the United States. Bet you they don't get past 4. And this is a counting problem. If I have 200 million lives, I can count what is the most common 6-drug, 7-drug, 8-drug combination in the United States. And what happens if you go from a specific 7-drug combination to an 8-drug combination. Another example on the insights front is looking at patient forums. There's a group called inspire.com, which is a company, about 1 million people talking about their health issues. And we have a partnership with them. We analyze their content, and based on that, we get the patient perspective. And we found a new adverse event of oncology drug. And it's a cutaneous adverse event of an oncology drug. And it's just, oncologist is not going to ask about that, and the dermatologist is not going to ask about the oncology treatment that the patient is receiving. And these are the kinds of things that fall through the crack because the doctors don't ask about. The third bucket is about making predictions. And I feel strongly that in healthcare, predictions have to be about something in the future. When I chat with my CS friends, I often hear a sentence such as, I looked at an image and I predict it's a dog. No, come on, that's not a prediction. The thing was a dog before you said it's a dog. It's a classification. But in colloquial speaking, there's lots of papers where people report predictive accuracy of a classification model. To me, that makes no sense. Prediction is about, I tell you tomorrow's temperature, and then you check if I got it right. So predictions have to be about something in the future, and those are the ones that are helpful in healthcare. And all of this is to bring AI to the clinic safely and ethically in 3 to 5 years. So I lead something called a program for AI in healthcare at our university and our health center, with the focus on bringing it to the clinic and caring equally about safety and the ethics of it as much as about the technical feats of deploying. So that's the framing, but that's the work in my team. And I'll give you one examples of each one. I can even do a live demo of our search engine that drives the bedside clinical consults service and so on. And then, so all of that is sort of optional. And then the main thing is my view about good machine learning for better healthcare. Because you guys are all experts in computation. If I can convince even 2% of you, which I think will add up to 1 human, with 2 people, then that's worth the time spent. So this is my attempt at giving you all of healthcare in one slide. It starts with an individual or their family. And typically these days, if somebody has a problem, the first response is they search. Like if you had any medical issue remotely, that before going to the doctor, like you would open a browser and search. As a second step, you might end up at a clinician or a health facility or a hospital. And if you do happen to go there, there'll be this third party in the mix called insurance, which for the most part, most people don't understand how it works and have no idea who pays who, how much, and when. Then there's the drugstore, because if you go to the hospital, one of 3 things happen. You either get a prescription, they do a procedure on you, or they ask you to come back later. Then there are pharmas, biotechs, device manufacturers that sell things to the healthcare providers. And then there are vendors that sell to them. And then everybody's trying to reach to everybody else, trying to reach to the individual directly, advertising on the web, talking to insurance to make sure whatever it is that they're hawking is worthwhile and should be paid for, and the government trying to regulate this mess. The reason to have such a mind map in your head is when you get data of whatever kind, it'll be produced by one of these actors in the ecosystem. The incentives of those actors will influence the data that are collected. And without knowing that, if you start drawing inferences from that, you're guaranteed to make a mistake. So you have to know who pays who, how much, when, and why, in order to interpret the data. Now, to a computer scientist, it's like, well, what is he talking about? If you have data, you have your rows, you have your columns, but the values you get in your columns are dictated by the incentives that drive that, and you have to understand that before you begin data analysis. Yes?
And vendors is where you have all your medical devices as well, or not?
You could put them under the pharma biotech, you could put them under vendor. I mean, each of these icons is multi-billion-dollar segments. And I could literally rattle off 100 companies in multiple sectors. So the goal is to have this framework that whenever you get a data set, Question, who created it? Why did they create it? Why did they collect that data? And what is their incentive? All right. So that's healthcare, or I would say the conveyor belts of the healthcare system. The second big thing is healthcare happens over time. And that's also something that's often ignored. So you have a patient, left to right is the timeline, and things happen to them. Then you'll have some recording of that, either in the form of the disease codes assigned to them, the prescriptions that were given to them, the procedures done to them, imaging, billing, and claims. If they're in the ICU, that's the point at which you'll get some streaming data, good sampling close in time. Somebody somewhere will definitely say the word genome, and it's typically measured just once. And we can assume it's stable over time. It's an assumption. You could even argue that you get the genome from your cheek and you get the genome from your gut. You might get a different genome. Most people find that shocking. And then you have people over time. So what matters is doing things, and I'll have to, the pointer won't work yet, is to apply machine learning using whatever data you have to tell me something about what's going to happen next. A lot of machine learning is geared towards point solutions. As in, I'll read this image and say there's a fracture. And look, my computer can do that. Like, okay, that's great, but that's not a problem anybody needs solved. Or you look at an X-ray and say it's pneumonia or not. Who cares? Because if there's any slightest doubt of pneumonia, we'll give an antibiotic anyway because it costs $20. And so then people invoke this idea that, oh, it's going to help the developing countries where there's no radiologist and all that kind of warm, fuzzy stuff. There's truth to that. But unless you understand the ecosystem, it's kind of out of place. Okay. And then these data, so now just pay loose attention to the colors. I'm going to take this matrix, and I'm going to rotate it this way and this way. So there's a lot of hype around data. And I want you to think about the three axes: people, features, and time. So if you're working with EHR data, you would have, give or take, 2 million, 3 million, 5 million lives as rows. You would have about 30,000 unique features that you would have access to, and then about 8 to 10 years longitudinal data. If you're working with insurance claims, you have a smaller feature space, typically 10 to 15,000. There's about 4,900 FDA-approved drugs, 1,500 commonly occurring ICD-9 codes, and so on. And you have more longitudinal coverage, and you'll have more rows. You can go into the hundreds of millions. If you're working with variables, things I call the quantified self-movement, there I would argue that we don't even know what a feature is. So how many of you have used a variable like a Fitbit or an Apple Watch and gotten a step count at some point? What you're getting is, from that device, is the normalized voltage of one-dimensional acceleration. Then some programmer who you've never met applies a transformation to it and outputs an integer, which you trust as the number of steps you took. If you get access to two such devices, put one on the left hand, one on the right hand, by the end of the day, they'll differ by 30%. So we don't even know what the features are in that particular step. And then you go into the genome, microbiome, and all of that stuff. You typically have 10, 15,000 samples, as in rows, patients, and you have the feature space in the millions and no temporal resolution. Statisticians call that variable under resolution. If you have 6 million features and 10,000 samples, most models will fit. But there's no guarantee that it's the right one. So the reason I'm giving you this contrarian view is that there's a lot of hype in the media about machine learning and AI just revolutionizing healthcare. There's some truth to that statement, But a lot of that hype is just people not understanding what are the problems worth solving. And what I want to focus on is what are the problems worth solving. So I believe that you can point the textbook of machine learning, if there is such a thing, to solve problems in three broad buckets: to advance the science of medicine, to advance the practice of medicine, or advance the business of medicine, delivery of medicine. It is a fallacy to assume that advances in the science of medicine result in immediate advances in the practice or the business. That is what the New York Times would want you to believe. That is what the scientists that are writing science and nature papers would want you to believe. But if you believe that, then go to the Wayback Machine and look at the headlines when the genome happened in year 2000. Cancer was supposed to be cured a decade ago. It was a huge accomplishment in advancing the science of medicine, sequencing the genome, and had to be done. But it was sold as it will advance the practice of medicine in a decade. It didn't happen. 2 decades later, we're still measuring. And that happens all the time. All right, so now how do we find problems worth solving? So the columns in this little table are the same things on the previous slide. The science, the practice, and the business, which I just replaced with delivery of care. And then the rows are labels that doctors use. A machine learning or a computer scientist would label the first row as solving a classification problem. The second row will be solving a prediction problem. And the third row would be solving an action recommendation problem, which the doctor will say diagnostic, prognostic, therapeutic. It's the same thing. So what I believe, and this is where we get into opinions now, is the problems worth solving are here if you want impact in the next 3 to 5 years. Absolutely, the science needs to be advanced so that you get impact 15, 20 years later. But if you're a computer scientist wanting to make an impact in the next 3 to 5 years, pointing your energy at solving problems that advance the science is going to lead to disappointment. It's worthwhile solving those problems, but you got to be realistic about your payoff. And particularly those problems that are either classification or prediction problems in practice and delivery, if you can connect them with actions, that's when you make real impact. I'm going to give you one example just to hit home that point. So we're going to look at a classification problem on the practice side and connect it to an action. That's why that particular arrow is in red. So this is joint work with Joshua Nolis, who's a collaborator of mine, and the Familial Hypercholesterolemia Foundation, which is a patient advocacy group. Lots of people involved in this effort, at least 25 or so. And I'm only going to give you the high-level version of it. So this particular disease, it's a genetic condition, as you can guess. The estimated prevalence in the United States is about 1 in 250. If we just, walk down Admiralty Way and chatted up 250 people, one of them will probably have this condition. In a lipid clinic, as in someone who has high lipids and therefore show up at the health system, it's about 1 in 90 to 1 in 100, depending on who you ask. Now, in order to find that one person, I would have to genotype or sequence 100 people. So at even $1,000 a genome, I have to spend $100,000 to find that one case. There's a very effective drug for this disease, and insurance will happily pay for it if you're confirmed with a genetic diagnosis. The drug costs $12,000 to $14,000 a year. They're called PCSK9 inhibitor drugs. And right now, the choice in front of a doctor is spend $100,000 to find one case, which will then cost $12,000 to $14,000 to the insurer in perpetuity. No insurer is willing to fund that deal, because even at $3,000 a year profit, with that much cost to find one case, their break even is 33 to 35 years. So what we did is we took a few cases that we knew were positives, 110, and we came up with 300 controls. I put them in sneer quotes because they're not really controls. They're people who have high cholesterol but are not having the genetic version of the disease. We train a classifier, okay, like elementary stuff. First year CS students can do this stuff. And the classifier got decent PPV, about 0.79, good recall. This is all cross validation, so okay, great. Do a high five, but can be short. So we then applied that classifier to 71,000 patients in our lipid clinic, and it flagged about 2,000 of them. And then we reviewed the top 100. And 79 happened to match the current diagnostic criteria. So we would want to sequence them, or we believe that they're for most part positives. Okay, so that's reassuring. Then we went to another health system that had 466 genetically confirmed cases. And without looking at the sequence, just look at the EHR data, we've nailed 77% of them. Okay, so now let's do the math again. Patient walks in, 100 people walk in, I run my classifier, it flags a few people, and I'm correct about 8 out of 10 times, or 7 out of 10 times, to be conservative. So if I sequence 10 people, I'll spend $10,000. I'll find 7 true cases, which to the pharma company will accrue $84,000 of recurring annual revenue. Now, if you're a marketing person at that company, and I say, can you fund $10,000 of genetic testing so that you get $84,000 of recurring annual business for life? What would you do? It's a no-brainer. As a companion diagnostic. If you're an insurer and you treat 7 people and spend $84,000 for 5 years consecutively, you prevent 3 heart attacks. It's a great deal if you're an insurer. And it's awesome for the patient because nobody was getting treated. And now 7 people will get treated. So this is what I call an example of using very simple machine learning to take out the friction between the patient, payer, and provider triad. This triangle has a lot of tension in it. People want what's the best for them. Payers want to pay for what's good overall for their whole covered population or society writ large. And providers, doctors genuinely want to do the right thing for the patient. By and large, I mean, of course, there'll be exceptions, but by and large, doctors really do want to do the right thing. And so if you can use algorithms to realign the stress in this system, you can make real impact in a short amount of time. So that's just one such example. And I have 4 other examples about, predicting cardiovascular conditions, predicting death, predicting cost, predicting delayed healing wounds, and a whole bunch of other stuff. But that's sort of the gist of it. All right, so I'll pause here. We're at about half time. That's what I really came here to talk about. So whenever I get hold of a bunch of smart computer scientists, they get this spiel about where should you point your energy if you choose to work in healthcare. And after that, I have examples of how my group has chosen to spend its energy. And that's not as important as the larger framing of the problem. Okay. So I told you the clinical questions. Yeah.
Sure. Just a quick question about, so the point that you made, so basically, I mean, from the computer science point of view, what you did is improve the diagnostic accuracy of the system for a specific case, right?
Right.
And so is it, what you are saying is that, I mean, one can say it's always good to increase diagnostic accuracy of all the diseases, so that's what should our energy go for. But are you also saying that, you should also basically consider more kind of economic fundamentals and see whether the improvement you are going to get from the type of diagnostic, let's say better classifiers, is going to translate into something that will happen in practice?
Yeah, so the main point is for whatever classification or prediction you can make, tie it with a concrete action that the health system can take. So in this particular case, the fact that a classifier flags somebody results in a concrete action saying sequence that person and you'll be correct 7 out of 10 times. You could have very simple classify, or let's look at a prediction example on the delivery side, like an extreme commercial example. No shows for clinical appointments. They cost health systems millions of dollars. If there's an MRI appointment and you don't show up, their machine is sitting idle. Those machines cost millions. The facility that houses them has a huge capital expense. And every minute or every hour the machine is sitting idle, they're losing money. But have you ever heard of a health system that uses a predictive model on who's going to be a no-show and based on that double book MRI appointment? Why not? It's a solved problem in the airline industry. You had a question?
Well, you asked a semi-rhetorical question, who has predictive models to predict no-shows? We do.
Yeah, so,
It seemed like low-hanging fruit, so we did.
Exactly. Exactly. And I mean, these are problems that computer science professionals solve for homework in grad school. All right. So now I'll walk you through 3 examples in one in each bucket. So on the clinical questions front, this service, which we call our green button service, and the reason behind that is when in 2014 or something, we wrote that vision paper, the one with that red bar over there, envisioning an actual button in the EHR that a doctor could press and find a summary of similar patients. And then we were choosing to assign a color to it. And Blue Button is taken. Blue Button is the project that gives you a download of your own data, pushed by the Department of Veterans Affairs. You can't have red in healthcare. And so then the question for ourselves was, what is the color of evidence? Well, that should be the clear button.
I think yellow.
Yellow is still warning. But then we figured that no computer scientist or IT person would click on the clear button because it deletes your whole screen. And then brown was offered up, but then I'm brown, and then it has a whole bunch of racial connotations, so we kind of stayed away from that. And then UPS could sue us. And so we settled on green. It's kind of a fun side story. And so the idea there is literally what happened to patients like mine. And at this URL is a 2.5-minute video, which I can try playing because I'm online and I'm connected. So let's see if that works. Here.
Cardiologist seeing a new patient with an incidental diagnosis of atrial septal aneurysm. You wonder about the need for anticoagulation for such a patient and read the literature to find that there's limited evidence on how to manage such a case. How do you proceed with care of this patient? Physicians often face such uncertain situations for many reasons, such as a study answering the question has not been done yet, the available evidence is unreliable, or the evidence does not apply to their patient. In such situations, wouldn't it be amazing if physicians could leverage the experience of millions of past patient encounters instead of relying on anecdotal experiences or input from colleagues? The Clinical Informatics Consult makes it possible to aggregate data from over 150 million patient charts and obtain a summary of what happened in practice. These insights, derived from the accumulated experiences of other patients just like yours, enable precision in the practice of medicine. To provide our service, we first clean up the data present in the electronic health record. Then, using a novel search engine developed at Stanford, we generate patient cohorts in seconds and perform statistical analyses to provide an answer for your clinical question within days. To submit your request, all you need to do is email a question to greenbutton@stanford.edu with the following information: patient population of interest, intervention or exposure to study, description of the cohort you want to compare with, outcome of interest, and time frame over which the analysis should occur. Once we receive the consult question, one of our clinicians will work with you to refine the question. Our team will then perform the analysis and generate a report with an interpretation of what the results mean for your patient. Our clinicians will discuss the report with you and clarify any follow-up questions. Our service has already been used to answer diverse questions across multiple subspecialties. Realizing the vision of the green button, the power of aggregate patient data can now be brought to the bedside. The next time you are in an uncertain clinical situation and wonder what happened to other patients like mine, we'd love to help. To request a consult and see some example consults and reports, visit us at greenbutton.stanford.edu.
All right, so that also ensures that that section stays to exactly 2.5 minutes with good reproducibility. So this is the search engine mentioned. It's something we wrote from scratch. A lot of great CS behind the scenes, which I'm happy to talk about one-on-one. The gist of it is it implements Allen interval algebra rather than relational algebra. There's no SQL in the back end. And as you're searching, it is aware of the hierarchy of concepts. So for example, drugs, you can have simvastatin, which is a kind of statin, which is an anti-lipid drug. So you can search for patients who are taking an anti-lipid drug. And the system internally will expand all of them to all the different enumerations of the statins and the other one. Same thing for diseases, same thing for procedures, and so on. So it understands knowledge graphs. I made a reference to ontologies, so that's where I spent about a decade before switching gears. And second, it has a funny way of managing memory. So we can actually push 3 million patients worth of data into less than 20 gigs of RAM and up to the proven data, which is 140 million or 200 million lives. We can shard it over multiple instances and still get millisecond response times, and run it on the cloud and so on. So scaled with a credit card and that kind of stuff. So the language is actually worth looking at. We call it temporal query language because we didn't have another name for it. And the search engine is called Atlas for Advanced Temporal Language Aided Search. If you build a cohort of patients, you get a sort of a visual view of their timeline and keep going back to the timeline because healthcare happens over time. And you want to be able to see what happened after what other thing and so on. And the language constructs, it's a domain-specific query language in the genetic sense, and you can search for patients with no history of a disease, and it knows what it means in terms of the timeline. What does no history of mean? And you can do intersections, as in have two conditions concurrently, or one after the other, and so on. And that's the URL where you can see a demo of just the search engine. There's lots of open questions in this service. So potentially, what are other uses of the search engine? Well, we're using it to answer bedside questions based on similar patients. When I show this to our finance people, they want to compute quality metrics. What fraction of people with pneumonia got an antibiotic, that kind of stuff. And then on a scientific level, like what is really useful to give back to the doctor? Just a descriptive summary of what happened to patients in the past? Should we do any population level estimation of what might happen, like solve an inference problem at the population level? Should we attempt to personalize that inference problem and base it on a narrower set of similar patients, also known as heterogeneous treatment effect estimation or conditional average treatment effect estimation, depending on which literature you read? And then, is patient level prediction useful? Because you can solve a prediction problem relatively easily and say, for this person, the 5-year risk of a heart attack is whatever. But then the minute you make the prediction and show it, they're going to respond to that and do something different, which is going to invalidate your prediction. Because the prediction is made assuming no change happens. They're going to make a treatment decision based on that. So how do you reconcile that? There's a lot of informatics work that needs to be done on how do you know a patient had a condition, like diabetics? How do you find patients with diabetes? You can do that writing rules. You can do that using supervised learning. There's a lot of representation learning projects that we have in terms of trying to figure out how do I take clinical notes, lab data, ICD-9 codes, prescriptions, and turn that into a dense fixed length vector representation so that I can use that for matching patients, finding similar patients, and so on. Then the population level inference and the personalized treatment effect estimates, I already alluded to that. And then, what's the financial viability? Who's going to pay for this? Because if it costs $5,000 to get a report of similar patients, no one's going to use it. If it's $5, consumers might just want it just for fun to see what happened to similar patients. And the truth is somewhere in the middle, and we don't know where it is. So we've done about 90 consults as of now, and this is just a breakdown of how many of them were causal inference questions, how many of them were survival analysis questions, how many of them were just exploratory. Exploratory are the ones that are of the form, how often does something happen? And there's a few examples. So a causal one was in patients prescribed ibuprofen versus those were given acetaminophen. Is there a difference in peak glucose? Which is very relevant for inpatient pain management. Another example of the survival one is in adults with hypertrophic cardiomyopathy treated with beta blockers or calcium channel blockers. What is the time to heart failure? It's great. It's descriptive. It's a survival analysis. The minute I show it to them, I know they're going to say, oh, it's longer time to heart failure with calcium channel blockers, therefore they must be good. And how do you convey that? No, that's not the interpretation. And then exploratory in patients who underwent the procalcitonin test that's positive, how many times do they get a positive blood culture? So wide variety of questions. Right, so I'll pause there for a second before switching into the next one.
Just a quick question. So how many samples again do you have?
The patients?
Patients.
So about 3 million Stanford records and 140 million medical claims. So depending on the question, we go to one or the other source. So decent sized data sets. All right. So I told you about, doctors not asking some of the questions they should be asking. And I'm going to actually show you a very concrete example of that. So this is a project I did with the Observational Health Data Science and Informatics group. It's based out of Columbia. George Herbsack at Columbia's Department of Biomedical Informatics is kind of the main coordinator. And what we're looking at is how is diabetes treated worldwide? The innermost circle is the first drug a diabetic gets after diagnosis. The second circle is the second drug, third, fourth, and so on. The color tells you which drug. This is done with 250 million patients worth of data international. And we did this for diabetes, hypertension, and depression. I'm only showing you diabetes. So the guidelines for diabetes management say that for a new person diagnosed, you should begin treatment with diabetes. And so the question we're asking is, how often does that happen? And it's about 75.5%, so life works as advertised. For those that are not getting metformin as their first drug, there's a very obvious reason. Their kidney function is not good, so they should not be on metformin, they're on something else. No problem. But if your blood glucose is not controlled in 90 or 100 days or 3 to 4 months, the guidelines from both the American Diabetes Association and the American Association for Endocrinology say you should pick a second line drug. And then there's 4 or 5 pages of gobbledygook saying just pick a drug, but they'll not have a clear recommendation which one. And you can see what doctors do. They pick one. And you can see the second circle. It's a nice, roughly even distribution between the different choices. So they follow what the guideline says, is pick a second line drug, and they pick at random, practically. So we asked the question, so this itself was shocking. This came in the PNAS because no one had characterized how are these very common diseases really treated worldwide. Like we just did not know. This is descriptive statistics, no inference, just solving a counting problem. And the next question we ask is, does it work? So people go from metformin to one of these three, like what happens? So again, it's a collaboration between 7 sites across multiple countries. And we ask if you go from metformin to glipizide versus sitagliptin versus pioglitazone, which one gets your A1C down faster? And if you look at the plot, I mean, you don't need to be a statistician, there's not a huge difference. We then asked which ones are different in terms of their adverse event profile, in terms of cardiac, renal, and ophthalmic side effects. Turns out one of them has a slight difference, about 12% difference, in the rate at which myocardial infarctions happen in people treated with that drug. So just asking a descriptive question, which the guidelines say is needed to be answered. There is no RCT that conclusively answers this question. And as a collaborative group of informatics professionals, we could query 146 million patients worth of data to put some hard numbers on it. Okay. Now let's get into a little bit more exploratory territory. What diseases follow each other? As in, if you have acne, what's the chance you get eczema? Kind of a trivial sounding question, but there are multi-billion-dollar industries or companies that are geared towards treating acne and treating eczema, and they don't talk to each other. So what we did was we had these 140 million or so patients across all 50 states. So we look at all patients who had more than 2 encounters with the health system in year 2009, and then we did the same thing in 10, 11, 12, and so on for 5 consecutive years. And we just created a matrix of patients who have a disease and people like them who do not have the disease. So people with acne, people without acne, people with diabetes, without diabetes. And then the columns are the other diseases that they have. And then we do a state-by-state analysis to see that if you have whatever condition you're looking at as this yellow column, disease of interest, we just regress all these other columns against that to see what's associated with this particular disease. State by state, and then over 5 consecutive years. And I only want to believe those associations that are stable over geography and are stable over time. And that gives us this many disease by disease pairs. And so I was looking at, I was speaking about acne given eczema. There's definitely something going on, and definitely something going on in Texas. Probably some data anomaly there. But there's an association that if you have acne or if you have eczema, you're high chance of getting acne, or the other way around. And acquired hypothyroidism given Down syndrome, this is a known association. We see it in pretty much all the states. And then we found a few new ones, which we can't explain. One of the associations is such that the one drug has lots of treatments, one disease has lots of treatments, the other one doesn't. And they appear to follow each other. So there's some common biology going on there. Right, so that's basically fishing expeditions using lots of data in an attempt to drive the science of medicine. And then I'll close with an example of predictive modeling, and I'll go straight to the heart of the problem. I often joke in my classes that there's only 2 outcomes in healthcare, which is survival and cost. And the ultimate one is survival at what cost? And so I'll focus on mortality and death as the outcome of interest. So what we're looking at is a map of palliative care in the United States. I promise you there's nothing to do with politics in this map, but there is a strong correlation. And palliative care is commonly interpreted as end of life, but that's not what all of palliative care is. Palliative care is basically to use medicine to make the patient comfortable. And it could be invoked when someone's going a transplant or a blood transplant or a bone marrow transplant and so on. It could be invoked towards when you're undergoing intensive chemotherapy or towards at end of life. So the sad statistics about palliative care are that about 90% of hospitals in the US, which are larger than 300 beds, offer palliative care. There's about 6,000 hospitals in the US. And the estimate is that between 7 to 8% of people being admitted to a hospital need palliative. About half of that get it. Countrywide statistics. So at Stanford, the way palliative care works is there's a person admitted, and if their treating physician feels the need for palliative care, they will pull the palliative care specialist to see their patient. This is what happens. About 131,000 people have died in our hospital in the past, 10, 15 years. We asked the question, how many of them got palliative care? 3.55%, like a smidge above average. And then we asked how many of them get it 6 months prior. Yeah. And it's abysmal. So that summarizes the nature of the problem. Palliative care is too little, it's too late. Now there's randomized controlled trial-based evidence that if you use palliative care, patients live longer, they're happier, and they cost less. And proved in a randomized control trial. But we still don't do it. So we said, all right, what can I do? So remember that now I'm going to solve a prediction problem and tie it to a concrete action. So we said, all right, if we could have a computer read through everybody's record, and I want to learn a function that flags the patient to the palliative care doctor and flip the model from a pull to a push. And so the palliative care doctor now goes to the treating physician and say, I think I can help this patient. What do you think? Now you've got to get into a little bit of the dynamics of how doctors think. When oncologists are asked to estimate survival for their patients, they overestimate it by 7-fold. And they have to. Like if you're an oncologist, in order to get into work, you have to have that delusional level of optimism, because otherwise you can't go into work and keep losing patient after patient. Like you just have to be that way. But that's not in the best interest of the patient after a certain point in time. But as a human, you can't just make that flip from one mode to the other. So that's where we want to plug in a computer in the loop. So what we did is we built a model that at a given point in the timeline makes a prediction for someone dying in the next 3 to 12 months. Why 3 to 12? So here's the notion of lead time coming in. Most models get evaluated based on their positive predictive value, AURC, AUPRC, calibration and all that stuff. But if you tell me someone is going to die with very high positive predictive value, very high sensitivity and specificity 24 hours before they die, it is too late. If you give a list of 100 people to the health system and say, call them, it takes them 90 days to figure that out. Like who's going to call, when, how do you track them down, and so on. So you need enough time for the logistics, the gears of the health system to turn for the action to happen. And our best guess is that it's going to be about three months. The 12-month comes from the fact that most people beyond, if you still got a year to live, you're not ready to talk about dying. Right? As most humans, you want to think positively. So this is a hypothesis, but in talking to clinicians, we figured out that 3 to 12 months might be the sweet spot. And then we build a model. What I'm showing you is area under the precision recall curve for a gradient boosted model and a lasso. And then on the right are the calibration plots. Some of you might have heard about deep learning models that our group built, and there's like 10 newspaper articles about it. That model is not deployed. The deployed model is a gradient boosted model because I can run it on my laptop. I don't need a GPU. I don't need a GPU to train. And so the way things work, we have our historical data where we learn the models. When patients get admitted, we get a daily feed. 2 a.m., we run the model, we write the results back. By morning, 8 a.m., an email goes out to the chief of palliative care that of the people who got admitted, you need to see these 6. She then spends about 90 minutes deciding whether it is truly worth following up or not. 90 seconds per case to decide whether it's truly worth following up. She follows up about 66-70% of the cases. And then once she does follow up, it's about 15 to 17 minutes to track down the treating physician and have a quick conversation with them about them to say, okay, now let's have the palliative care goals of care conversation with your patient and get them into scheduling. All right, so the reason I'm sort of going into this much level of detail is that what makes a model useful in terms of its utility is not always just the positive predictive value or the recall or anything of that sort. It's other things. It's things like who's going to take the action? How much lead time do they need to take the action? What is the cost of that action? What is the capacity for taking that action? Because I can stuff Stephanie Harmon, who's the palliative care chief, her pipeline with a lot of cases. But their capacity is about 10 max reviews a day. So that for me translates to I need to worry about precision at K or PPV at 10. Because if every other prediction after that is wrong, it doesn't matter. And sort of just to hit home that point, how many of you have done a Google search today before coming here? Okay, what's the PPV of a Google search? 0. Because if you search, you get 100, 200,000 results. And the top 3 are relevant. So absolute positive predictive value is 3 divided by 100,000, which is 0.
But you never look at the second page.
Exactly. So that is precision at 3 is what matters. The top 3 hits. Maybe, first page for people who are computer scientists. Nobody goes to the second page. So you need to optimize for precision at K. A multi-billion-dollar computer industry exists for PPV at 3, with overall PPV at 0. But we write papers arguing about improvements in 1-point PPV overall. Makes no sense. Okay, so to wrap it up, when you see a model, ask about what is the kind of use case at hand. Is it operational? Is it medical? Is it diagnostic, prognostic, therapy? Fill out that little grid. Then who will decide on the action to take? And do you have any hope of them listening to you? And then what are the assumptions you're making about the existence of an alternative action? About the need for interpretability of the model. So for this, I'll come back to interpretability in a second. And then the incentives and the ability to take that action. You need to verify these assumptions. And interpretability is a nice example. Anytime I hear a request for interpretability, it means 2 things. One, the doctor wants you out of their office and go away. Second, what they're really asking is that, can I trust this? And the request for interpretability is just a substituted question for the real question about, can I trust it? Because doctors use things they don't understand all the time. For the majority of the drugs they use and prescribe, we have no idea how they work. 0, no idea. But we use them because they've been proven in randomized, controlled, prospective settings to actually work. So when they ask for interpretability, what's really being asked, can you prove that this works? That you can test without making a activation map or anything of that funny business, and just test it prospectively to say it works. So whenever somebody asks for interpretability, your alarm should go off saying, okay, what is it they really want? Because by creating abstract art in the form of an activation map of a deep neural net, it doesn't really solve any problem. All right, so to close out, all of this is to bring AI to the clinic safely and ethically in 3 to 5 years. We've done stuff with large search companies like Google. This is a paper that got a decent amount of flack on Twitter by Dave and his friends. This is the deep learning work that got covered heavily in the press about predicting mortality. Every reporter I spoke to, I told them that it doesn't matter that it's a deep neural net, but they always wanted to write about that and not the real model. And then we write about safety, we worry about ethics, and so on. All right, I'll stop here. Lots of people in the team. It's not a one-man show, obviously. Funding from a variety of sources. And then we wrote this paper in 2014, and I joked that, yes, the button is actually green, 2017. All right, I'll stop here.
I start the opposite way. Start with the problem. Clinicians wanting to. So I was curious about things. How is the messaging delivered from the person who gets the report that goes to primary care? How do they approach that? What is the messaging like?
Face to face.
And also, how does that MD usually or respond to the news of, we think a model says this patient, and I trust that this patient has.
That's a great question. It all boils down to trust. So our internal medicine service line that is on good terms with the palliative care service, they love it. Okay? They will listen and act. There are certain service lines, which I will not name, who basically say, go away, we're making too much money, I don't want you in my hair. So it could go either way. And so that's why I bring it back to you have to know what are the assumptions you're making about their incentive to take action. So voluntary or not, the people who listen are the ones who have some incentive, either personal incentive to do the right thing, or a financial incentive, or a top-down directive from quality or compliance or whoever. But you need at least one incentive for them to listen. Yeah.
You see the space for users, like, to use this data, not without involving doctors in between, or just patients that they could make some decisions. I think they have really a huge interest.
So that's something I've gone back and forth over a lot. That what if we could just put such a search engine online for anybody to use? Like, philosophically, I want to do that, but I run into a lot of problems. And the two broad buckets of problems are, it could be construed as practicing medicine. That you can usually argue away. I mean, you put a disclaimer and a click-through that says it's not a practice of medicine advisory, blah, blah, blah. You can avoid that problem. The second problem is that the current search engine interface is essentially a command prompt. And it's on the web, but it's a command line. And it's Lisp-like syntax. And the number of humans who can write Lisp-like syntax in a language that is not widely used is very small. And it's easy to make mistakes in such arcane query language. So there's a UI problem. Like, how do I get a person to the search engine? And right now our UI is another human who understands medicine and understands the search.
Of course, that could be probably overcome.
Absolutely. I don't know enough UI and computer science literature or expertise to solve that problem and bridge it, but yes, I believe it can be done.
So I have kind of a general question about incentives. So we've heard that the healthcare system very bad in a sense that we spend a lot solving out. So do you think that overall the incentive structure in place are okay and do this kind of local interventions, maybe put a computer here and there, then basically the whole system will improve? Or some of these incentive incentives are so structurally bad that whatever you do, you cannot change the whole system around, basically.
So fortunately, at least as things stand right now, the macro level incentive structures have changed enough already to align the payer, the provider in the patient's interest. So the two-line version of that is previously a doctor would get treated based on how much they do, so fee for service. Now it's fee for value. So here's Nigam, here's $20,000. Keep him healthy, happy, and alive. 3 things. Because if he's dead, you get no business next year. If he's unhappy, you get a 3% penalty on your payment. And if he's unhealthy, you bear all the cost and the losses. So that's the macro level incentive, and there's always nuances at the individual level, but by and large, Medicare has already gone there. And commercial insurance follows Medicare with a 2 to 3 year lag. So by 2021, the majority of healthcare will be paid for by what's called a capitated payment structure and a shared savings, as in there's a fixed price to care for a population. If the overall cost of care is below that price, whatever is left is divided up by the insurer and the provider as shared savings or profit. I mean, that's just a euphemism for profit. Yeah.
Okay. I'm not really asking a question, just an opinion on interpretability. When you say that when we ask about interpretability, we really want to know whether we can trust the model or not. But I think if we think more, like we can see that the patient wants that the doctor can explain why he thinks, or the model why he thinks. Because if you are the patient, then some system and doctor says, oh, here is the 0.9 confidence score, and this is the treatment. I really would feel anxious, and maybe it will correlate with my improvement, right?
Yeah.
So basically, interpretability seems to be a good question in both in terms of representation learning, like in general machine learning, and both the effect on the improvement.
So I agree with half of that point, and I'll tell you which part and what I don't agree with. Interpretability is extremely useful to the technical specialist building the model and debugging them. Okay? No argument about that, because you need to know what the heck is going on to troubleshoot. The part about the patient wanting interpretability, I think what they really need is explainability. And I'll illustrate the distinction. So again, back to the Google search example. You do the search, you get some results. You see the link, and you see 3 gray lines underneath it of text. The process that produces that explanation, the snippet server, has nothing to do with PageRank. So you get the results, and then a separate process analyzes the first result, the second result, the third result, and give you an explanation saying, why is this sensible to be result number 1? So what's needed to make right decisions is, A, you know that your predictions are correct. And then second, you have explanations to get buy-in to take the necessary action.
But the best explanation should come from the model.
So if the explanation for the model is that the most predictive feature is the cube root of your age.
No. We don't have to limit ourselves to the most predictive features.
Right.
We
So
can try to find more abstract terms, like a model texting something, like saying, like outputting a text or something.
So explanations, totally on board. But the traditional question you get from a doctor about interpretability will be, what are the top 50 variables? It's a pissing contest. Don't go there. Yes.
I have a question about data. So I'm assuming that like this EHR or other types of data are not just available somewhere on the web.
They're not.
How do you get them, and how can I, as a PhD student, have access to some data?
So I get them because I work in a health system.
Yeah.
You said how can you get them as a patient?
No, as a PhD student.
As a student.
Who wants to, yeah.
USC, I think, has a med school now.
So I can go to them and
You go befriend the IT department of the med school, not the doctors, the IT department. They get you the data.
Yeah, but that's actually.
I don't think.
What?
So I want to jump off. I mean, you said that any student can do this as a homework problem. That assumes they've got the data.
Correct. Yes.
And it's been curated for them, like by a team of people who actually understand what's coming out of sensors or whatever. But so getting access to the data.
So yeah. So there's
it's not an easy thing.
Agreed. Agreed. So
That's like an entire field by itself.
yeah. So there'll be relational databases, there'll be notes, there'll be EKG feeds, and then a slew of random data models that are being thrown at you in terms of so there's definitely agony in traversing that space and getting to a nice clean data frame before you can actually begin the work. But that can be taught. And it's not that hard actually to understand what is this acronym soup and where are people coming from. It takes about 4 to 6 months to get up to speed. and to know what questions to ask given the data set that has been thrown at you. It's not free. I mean, it does take 4 to 6 months of investment, but in a 5-year PhD, it's not unreasonable.
But so if I want to befriend someone at the hospital, I can get access.
Pretty much. Yes.
So there's over 1 million papers published. I mean, newly published paper every year on PubMed alone. And there's no way people can, like, researchers, users can digest and like make the connections between these results.
Yep.
And you talk about it, you see in the next couple of years, maybe decade, we don't really see like solutions could really help the science of medicine. What about like these efforts on text mining, NLP over these scientific literatures and make the connections, facilitating sort of an automate some part of the research process?
So that I would categorize as an effort to advance the science of medicine.
Sure.
Definitely needed. What I would say is also needed is the equivalent of a fake news detection on PubMed. Because a lot of papers, I mean,
right.
This is garbage.
But yeah, but for CS, like it's sort of a ranking papers authors by authority or the prestige, these kind of things are sort of mature, right?
Yeah, or you could take even a slightly different view and say, I'm going to just rank a finding, like not a paper, not a researcher, not an institution, but you're saying that this protein binds to this other protein. I'll give you an overall confidence in that fact. And that's probably more useful because if you build me a knowledge base from the literature, I don't really care who did the, I mean, you do care for the politics and citing that person when you talk about the work and so on. But from an experimental design and thinking perspective, what I care about is, do I trust that relationship?
Yeah, I think that's the main communication cost when we work with these medical researchers on convincing them about how accurate the result is. Maybe we want to deliver, we just narrow down a search space, like from millions of papers to the thousands. That's the effort we make, but it's a little bit hard.
Yeah, I completely agree. It is a hard problem to convince somebody that your extraction of A binds to B is 90% accurate. It's a tough one.
Yeah, right.
Yeah.
There's the extraction accuracy, and there's also, the experiment. They also
Yeah, so extraction as in not just the text processing extraction, as in believability, as in given all the experiments, the quality of the methods, the number of contradictory findings, this factoid, can I trust it? Can I believe it? That's a very hard problem. It's a good CS problem.
One last question from there.
Thanks. I just have a question. So, for example, for the green button program, when the doctors come to use that service, they probably come to see those very rare kind of situation, very rare type of disease that they're not really sure about how to define or how to diagnose based on their experiences. Because it's very rare condition, probably that's the reason why they have not much of information on it. So out of that database you have for the green button, you said there are 3 million patients and 400 million other patients from the other
140, yeah.
Right.
Yeah.
So then, how much of those data sets actually includes very rare kind of information that's actually can be very helpful for the doctors usually?
That's a great question. So we worry about what is our coverage space. It's both good and bad news. The coverage space is poor because for a lot of conditions, there's just not enough sample size. So the last one I got, for example, was how many patients who have Hodgkin's lymphoma and then get cholangiocarcinoma. We have 2. So what am I going to do, right? The good news is that we were totally wrong in terms of what questions doctors would ask us. So the kinds of rare case questions are the minority. The majority of the questions out of the form, I just had a patient with a C-reactive protein of above 7. What's the top 5 things that happen in the next 4 months?
Isn't it just basically for very lazy doctors who doesn't really study for what should be done?
No, these are things that are not known. You'd be surprised how much of medicine is still guesswork. So, another simple one, a friend of mine had a premature baby. They needed to do some operation on her, and we're going to give furosemide, a diuretic. Okay, there's a study out there that says you give diuretic to preemies, it could lead to nephrocalcinosis, as in their kidneys gum up with calcium. Okay. That is known. The drug has a warning on it. This guy has a simple question. What's the risk to my kid? Just how often? Like, you're supposed to sign a piece of paper saying, I authorize you injecting a diuretic to my newborn child, and it will jam up the kidneys with calcium. And being able to say it's a 1 in 2 chance, or is 1 in 15,000, makes a big difference. In this case, it's 1 in 15,000. So you could happily sign. It took 3 lines of query.
It's a free service?
Right now, it's funded by the generosity of a philanthropic foundation. Yeah, I don't know how many people would want to know the answer if it was not free.
All right.
Right.
So we are out of time. Thank you, everyone, for being here today.